So welcome to this class. So now today I'm gonna do a brief introduction of the randomized experiment in the context of causal inference. Okay. So in causal inference, you are interested in investigating the effect of treatment over control on the outcome of y of interest. So these are the examples. So suppose we develop a new drug, right? Then we are interested in effect. What is the effect on the health outcome on the treatment? So then we need to compare, and then so T will be used. Okay. T will be used to denote the treatment indicator. So T equal 1 is treatment, T equal 0 is a control, right? So in some textbook, they use A to denote the treatment, to denote action, but they are essentially same thing. And I already use A to denote the sample set. So that's why I decide to use T. Okay. So then there's a two potential outcomes. So the key concept is the potential outcome concept. So the outcome may change depends on what your treatment, right? So the presumption is that we have a choice. So so the one presumption is that the unit was exposed to a particular action. The same unit could have been exposed to another action, right? So that's a kind of a presumption. So then we are kind of excluding, right? Say that what if I was born as a female? I was born as a female. That's not really something I can choose, right? So the presumption is that we have some choice. Okay. And interpreting causation as a deterministic relation means that. So a second point is that we are not really considering deterministic causality, okay? Because smoking, so when we say smoking can cause cancer, that means that smoking always, right? We are not really mean that smoking will always create a cancer, right? Because some people smoke a lot and still live healthy, right? So then the causality here means that we are talking about some kind of a probabilistic causation. Okay, so which means that a person is a smoker, probably cause B, means that the probability of the hair cell, right? B is the cancer, right? A is a smoke. Okay, so smoking, conditional probability of getting a cancer, conditional on smoking, is greater than the marginal probability of getting cancer, something like that. So that is a probabilistic statement, right? Rather than this deterministic statement. So that is the presumption. So you probably know this concept already, but there's a two type of data that you can think of. One is the randomized experiment, such as clinical trial, where the event for T equal 1 is completely determined by the person who designed the experiment, right? So we use some sort of random mechanism to get this decision. Observational study is different because the unit decided to treatment or control could be depends on other factors rather than a random mechanism. So for example, the physicians can have some guide, right? Some prescription, then participant may follow. So that's not really random mechanism. So to be rigorous, you can think of this superpopulation framework, where conceptually we have a world, right? The one is the so two possible potential outcome world. So one is the y under control, and the other one is distribution of y under treatment. So that is very conceptual level where you can imagine, right? Where you have a you could, what if you get treatment control, or what if you get control? So that is a concept. And then the random variable is defined in the model, and then the realization from the model is a finite population. So finite population, we have realized a value which does not necessarily we observe. So we have a realization yi1 and yi0. Okay. So I'm gonna, by the way, I'm gonna use a Zoom in the class always. So if you're not really feel comfortable, or you feel cold or something, you are welcome to use Zoom, and that to avoid spreading the virus. Okay. So finite population, we have a finite population. So we don't observe every element of finite population, because we only observe one of the two, right? So the actual sample, we observe t and y, which is y1 if t equal 1 and y0 if t equal 0. Okay. So that is the way we conceptualize the how we obtain the sample, right, from the potential outcome. So so two things different. This is the about random variable, but this part, so the only thing we observe is this sample level, right? We don't really observe population level. We only observe sample level data. So this is what we have. But what you are interested in is to make an inference about the parameter in the superpopulation model, right? So that's the usual thing, right? We use data, and we use data to infer about the population, right? Make an inference about the population. So so for each unit I in the sample, we observe xi and ti and yi, where yi is yi in ti. So so the fundamental problem is that we observe only one potential outcome for each unit. So it is fundamentally a missing data problem in some sense, right? We always observe one among the two, so that means the other one is missing. So in some literature, especially in philosophy, the unobserved potential outcome is called the counterfactual outcome. Okay, so counterfactual, right? The fact. So for example, t equal 1, the factual outcome is y1, right? So if t equal 1, then for unit I, then factual outcome is yi1. And so yi0 is the counterfactual outcome, right? So intuitively, if we could observe the counterfactual outcomes, then the difference is attributable to the treatment, right? So this is the before, this is after, right? So before the treatment and after the or control and I mean treatment. So then this difference is fundamentally a key parameter for that unit. However, this is impossible, right? So here's the so that is called sometimes called fundamental problem of causal inference. Is that it is impossible to estimate tau I, which is yi1 minus yi0 from the data, as we can only observe one potential outcome per participant, right? Okay, so that is the fundamental problem. So then if we have a problem, then it's good to try to think about solution, right? So we live on problems. So what would be the solution? Well, there could be two solutions. One is sometimes one is can be called a scientific solution. Okay, what is the scientific solution? So suppose we can use some gene manipulation or whatever to apply the other treatment, right? The other treatment to the same unit. How can we do that? Well, suppose we are able to obtain twins, genetically identical twins. Okay, then that means the effect, and then if I can, so if two units is exactly the same genetically, and then if we give treatment to one and treatment to zero, right? Then the difference would be really due to the treatment, right? So that is actually scientific solution. I mean, some cases it's possible, right? In for example, if you in the cell level, for example, I don't know, you if you are good at biology, you can use some gene technology to duplicate the cells and then apply the chemicals and something like that. So that is not really our expertise, right? We don't know how to do that. So we only care about we only know how to do statistically. So this is the statistical solution. Oops. Let's go on. So statistical solution is the do some randomization trick. Okay. So we'll see how the magic of randomization can be used to solve the fundamental problem of causal inference. Okay. So here's some parameters we want to define. So basically, unit level causal effect tau I is almost impossible, right? We cannot really do anything about one particular unit. No, because we don't observe both, right? So it's not possible, almost impossible. So what you can do is do some averaging. So population level, group level, we can do something. So okay, so this is a parameter. But because we have two different concepts of population, one is the finite population, the other one is the infinite population, which is model. So in the finite population level, we can define finite population parameter, which is finite population average treatment effect. So this is a individual level, right? Individual level treatment effect. And this is tau I is individual, right? So this is individual, but we average over the individual over the population. Then this is a population level population level average treatment effect, right? And then if n goes to infinity, then finite population becomes infinite population, right? So that is ATE, usually average treatment effect in the model. Okay. And there's actually other causal parameters, such as average treatment effect for the treated, or some conditional average treatment effect, which is conditional on particular group, right? Some age group or some gender, race, something like that. So, which is actually quite important in micro precision medicine or micro targeting. So, for example, Amazon, right? They are more interested in learning this kind of conditional treatment effect, so that they can provide more precise, treatment for each group. Okay. So now here's some description of the data. I mean problem. So data is what we have, right? Data is given. So we have IID observe the data over these pairs. I mean vector, which is xi, ti, yi, where yi is essentially observation. So this is notation could be confusing. So right. So what yi, well, I will use yi to denote observed, right? Observed random variable. And yi t is a potential outcome, which is a conceptual thing. So the causal parameter, so the parameter that we are interested in for causal inference is a function of potential outcome. Function means some expectation, for example. Okay. It's defined using potential outcome random variable. However, we do not observe the potential outcomes, right, directly. So the goal is to estimate the causal parameter, such as average treatment effect, from the observed data. So then we need to assume something. And what would be the assumption? Well, the first commonly used assumption, widely accepted assumption, is sometimes called Stuttgart assumption, stable unit treatment value assumption. So assumption one is that potential outcomes for an individual are not affected by treatment received or potential outcomes of other individuals. So it basically means independence, right? What you respond is independent from others, okay? Which is not usually true, right? If you know, people are connected, and so what others think may affect me, but as a start, right? In principle, we assume independence to make life easy. Secondly, measurement assumption two is sometimes called measurement consistency. So the measurement consistency means that we don't have any noise comes in the measurement. So potential outcome, okay. Sorry, this is TI. So basically, mathematically, this is the description of assumption. So I already used it right before, but to basically we use this as a fundamental key assumption, where so the left side is the observation, right? The right side is a potential outcome. So the observation we have is simply a linear. So one of the two potential outcomes, and there's nothing else, right? No other. So sometimes in survey, for example, if you ask something, then so what is your income, annual income? Then if you want to pretend you are richer than what you are really, so you may exaggerate your income, right? Something like that. So, but we are not really going to talk about this in this class. So basically, what your observation is either so right, your observation is so this is a realized potential outcome. The right side is a realized potential outcome, and ti equal to 1, then we should use observe this one. Ti equal to 0, then we'll observe yi 0. Okay. So identification formula. Identification it means that we want to use observed data to estimate parameter. And let me back up. So identification means how can we use observed data to develop unbiased or consistent of the causal parameter. So this is an important question, right? Because we only have observed data only. We only have observed data and some reasonable assumption. And then we should use the assumption to somehow develop the estimator. So, so that means eventually we wanna use this. We wanna come up obtain. This one is interesting because the right side is the expectation of the potential outcome, which is what we want, right? The left side is expected potential expectation of the observed data observation, which is what we have. So we want to make the connection between use from what we have to what we want, right? So that is a kind of identification strategy, and thus so we are this is the simplest possible identification strategy, but we because we use a strong assumption such as randomization. So in this case, because we use this strong assumption, then we can identify the parameter easily. But if we cannot really assume that, then it's more complicated. But anyway, so the first thing is to so under one is what? Stuba, right? Under Stuba, we obtain equation 2, which is the conditional expectation of what you have, right? Observation is equal to the conditional expectation of what you want, right? Potential outcome. So then we can bridge, right, from what you have to what you want. Okay, so here's a verbal description. The left-hand side is the conditional expectation in terms of the observation, while the right side is the hand side is the conditional expectation of in terms of the potential outcomes. So let's prove it. So the statement is really simple, right? It's very hard to come up with a simpler than this one, right? This is probably the simplest. So then means the proof should be simple too. You see. So okay. So the only assumption we have is y1 t plus 1 sorry. One minus t. Okay. So so we could start from right-hand side to show the equality to the left-hand side, or we could start from the left-hand side to show the equivalence to the right-hand side, right? So then, which direction you wanna will be easier? Do you think it's easier? You should start from complex to simple one, rather than start from simple to complex, right? So which one is the simple? right side is simple, right? Because the left-hand side is complex because you have this Stuba assumption, right? So let's start with a simple one. Okay. Oh no, start with complex one. Okay. Then, well, then we know how to, we know the definition. Right? Okay. And now, so t, small t, is either 1 or 0. So then you can actually t equal 1. Then if t equal 1, right? T equal 1, then you have 1, 1. So the second term is 0. So then you have basically expectation over y1 given t equal 1. And that is expected. Same way, expectation y0 given t equals 0. So then you can write it as a something exactly equal to y equal to t given t equal t for t. Okay. So that basically proves uh, this simple region. Okay. And now it comes a randomization. So we now assume that treatment is random. Okay. Suppose my treatment is random. Okay. Treatment assignment is completely random. Then what happened? Well, this is actually quite easy because we already proved the equality to here. Right? So this equality, we already proved this part, which is equation 2, right? So we already proved this equality. So all we want to is to show this. So we already proved this. And so what we want to show is this equality, right? This equality, we need to use some assumption, right? So we have to, because we haven't used this before. So we should use this condition, which makes sense because the definition of the conditional independence, the definition of independence is that the conditional expectation is equal to the unconditional expectation, right? So you get equality. Okay. So that is the first, so our first formal result for identification. Okay. So on the complete random mechanism, we were able to use, so as long as you use conditional expectation given the treatment, conditional expectation of your random variable given the treatment, you can estimate for the expectation of the potential parameter, potential outcome. Okay. So the implication, so this guy essentially give us to come up with give us an idea of how to estimate the average treatment effect. Because how can we so we are interested in, for example, expectation of the y1. Okay, how should we estimate this one? Well, you should use the conditional expectation of y, observed y, given t equal 1, right? So that is actually, so the sample version of this. So this guy is actually estimating the y1. Okay. And same way, this guy will estimate y0. So I think we can maybe use p, the convergence interval, to be more formal. But or you can just see that this is just unbiased. So we'll soon see that this is unbiased estimator. So this one is essentially the difference between sample mean of y among t equal 1 and sample mean of y among t equals 0, right? So that is very simple estimator, and but it's important. So if it is important, it has a name, right? So so the name is difference in mean estimate. Okay. Or time. Okay. Well, now what do you want to prove? Well, we are almost ready to prove, but let's be formal. So we want to show that expectation of tau is equal to tau, which is what is tau, by the way, is expectation of y1 minus expectation of y0, right? So this is what you want to show. Is to show this equal. So again, we should start from complex one to simple one, right? So from left to right. Okay. So let's take a look this one more carefully. Okay, let me so let's take a look at what this tau hat is. And 1 TIYI minus 1 and 0 1 minus TI YI. Okay. And then the usual thing is to do the business of right. So if I do that, because we have two random variables, so we want to separate out. So if you do conditional, this guy is here. Okay. So if you do take the conditional expectation given t, then ti is fixed. So then the only thing is that you, so then you have basically I equal to 1 and okay, expectation over ti, expectation over ti given t, something like that. Same. So we'll only say same, right? So I only have a space for two lines. So okay, how can we write it? So we should use t is either 1 or 0. Okay. So if t equal 1, then it stays. If t equals 0, then it goes away. Right? So so that means this whole thing is equal to expectation of y equal to 1 given ti equal to 1. Right? Because the conditional expectation given ti equal to 0 has a coefficient to 0. So the one after multiplication, it goes away. So that means you get so basically you get so then you and then you have, I think I kind of messed up. Can anyone help? I want to show I want to show this, but somehow okay. Yes. Okay, right. So I think so we there's a additional thing going on. So this guy, so there's no harm, still write it, and then Ti is equal to 1, given Ti equal to 1. And then by independence, this one is the equation 1, right? Which is 4. And this we, so basically this one is, we don't have a dependence on I. So that becomes, so here you have a denominator is N1, right? And then you have a summation over Ti, which is N1. So N1 cancels. And then the only thing left is this one. Does it clear? Is it clear? What do you need more explanation? Yeah, this is essentially an algebra using equation 4, right? Using this result, you should be able to show it. Okay, but here's a really interesting part. So the time, right? This is time. Could have a very interesting interpretation of regression interpretation, where you this is observed, right? Observed yi. So you regress on observed yi on ti, then the slope for ti is actually equal to time. Okay. Well, let me how to show that. Well, so basically regression, if you regression of yi on 1 and ti is equivalent to regression of yi on 1 minus ti. Right? The columns span are the same. It's just the writing, how you write the basis, right? So in other words, if you do write it as something like tau ti plus epsilon ei, could be written as alpha minus ti plus tau plus alpha ti plus ei. It's exactly so yeah. Maybe I should write use beta to make the notation more. Okay. So if you write it this way, So then same thing, right? Just but what is the advantage of using this basis? They are orthogonal, right? So you actually apply OLS each one. So regression of yi on 1 minus ti is what? The slope for 1 minus ti is basically, so my point is summation I equal to 1 to n 1 minus ti square, which is 1 minus ti inverse. If you do minus 1, but the relationship, so you basically should subtract. So this one is actually this guy, and this guy is this guy. So the beta here is actually, so which is tau hat is, so this is tau. So tau hat is subtract this coefficient by coefficient for this guy. So which is basically beta hat 1 minus beta hat 0, which is time. Well, you could just use old-fashioned way, right? This is a quadratic function, so the optimization is not really difficult. So you can just do a differentiation and solve it, and then you get a normal equation that then you should be able to show that tau hat is indeed time. This is another way using some matrix algebra and orthogonality. Okay. So now this is interesting. So what is going on? And here's a statistical interpretation. So this is I actually I really kind of feel proud about this part because this is new. So if you think that there's some superpopulation model behind, right? So suppose so tau, you can write tau as a mu1 minus mu0, right? Where mu1 is expectation of the potential outcome of y1, and mu0 is expectation of the potential y0, right? Then there's a model. So what kind of model you can think of? So the model for the potential outcome is actually a kind of bivariate. So my point is y1, y0 should follow some kind of mu1, mu0, sigma 11, sigma 10, sigma 00, right? So this is a reasonable assumption, model assumption you can think of, because I don't have any covariate here. So you just use this simple bivariate linear model type assumption. And then this is the model for the potential outcome. But there is a kind of a transformation of the potential outcome using the Stuba, right? So this guy, oops, what's going on? Okay. So this guy is these potential outcomes becomes an input to some kind of a box. And then from the box, your outcome is yi, right? You have a kind of box machine. Okay. So the you put yi1 and yi0 as an input. And then this box, which is this one, right? This machine produce yi. Of course, you have to have a ti too. So basically you have a your this is a very simple function, right? Very simple function. You have a potential outcome and ti as an input, and you output yi. And so then, but you know the mechanism. You know the mechanism for y and t. And the mechanism for yi is this one, this model. Okay. The mechanism for ti is basically completely random. 1 or 0 with the property p and 1 minus p, right? So then you can derive the model for yi. That is the basically idea. So how can you derive a base, by the way? Well, here's a, so okay. Let me write it again. Mu1 plus ei1 yi0 mu0 plus ei0. Okay. And then yi is basically ti yi1 plus 1 minus ti yi0. So that means okay. Oh, what am I doing? I shouldn't, right? So this one. Uh, okay. U0 plus. Okay. So you have a mean part, which is a ti mu1 plus 1 minus ti mu0 plus error part. Error part. So this is a mean part. And so this is a still random variable, random in function of random variable, which is ti, right? So, but what am I doing? But you can actually write mu0 plus mu1 minus mu0 ti plus ei. Okay, so here's a basically I was able to obtain this, right? Where what is equal to ti ei1 plus 1 minus ti ei0, right? This guy is this. But what we want to show, is that we want to show this, right? We want to show yi is mu0 plus tau ti plus ei, where ei has a mean 0 and variance sigma square, plus some sigma square. So we are almost there, but I don't have a space. So I need to add one more space. So on my page. So basically, this guy, right? So this guy, let's write it again. Yi is mu0 plus Ti mu1 minus mu0 plus Ei, where Ei is equal to Ti Ei1 plus 1 minus Ti Ei0. So this is actually I already show this, right? This is tau. Mu1 minus mu0 is nothing but tau. And what do you want to show? So what you want to show is that we need to check Ei equal to 0, and variance Ei is a sigma, which is for some sigma square. So how to show that? Well, same thing. Ei equal to okay. So if you do that, then conditional on Ti, the Ei is a conditional independent of Ti, and then Ti is equal to Ti is 0, right? So you can actually show that. And then variance of Ei is basically expectation of Ti plus variance, conditional variance. And the conditional expectation is 0. Condition on Ti, right? The Ei1 and Ei0 is 0 expectation. So this part is 0. And this part should be constant. So basically this guy, you can see that this guy is indeed P times sigma 1 square plus 1 minus P times sigma 0 square, where P is expectation of T. So if you reflect what we did here, is essentially the point is that if you have a superpopulation model for the potential outcome, and if you have a and you know the Stuba, right, mechanism of the, so that means your observational mechanism is known, then you are able to derive the distribution of your observation. That is a tip, yeah, that is a kind of key part. And then because your model now, so this is basically this is a sample model or a data model, right? Your model about data. This is what potential outcome model. Potential outcome model is a concept. You never really observe the potential outcome directly. So you cannot really verify your potential outcome. But from the potential outcome model, you can derive the sample model. And then nice thing about sample model is what? You observe a sample, right? You observe a sample. So you can do regression or whatever, so you can basically estimate the parameters in the sample model using the sample data. So that is the key part. And then the only thing is that the connection. It turns out that this particular parameter happen to be our parameter of interest, right? So we are lucky because tau is our goal, right? but we are able to derive the sample model, and the sample model contains the parameter of interest. So that means we don't have to worry about all this. As long as we believe this model is true, then you just feed the regression, and then the slope is what we want, right? So that is the what's going on here. Okay, now here's I'm going to use the same very similar to example. So here's a capital N equals 4. So this is a population, right? So the population now has two values. One is the y on the t equal 1. The other one is y on the t equals 0. Okay. So then this is tau I, tau 1, tau 2, tau 3, tau 4. And then population average treatment effect is average of these taus, so which is 2.5. But we don't observe the population, right? The problem is we don't observe. We never observe the potential outcomes jointly. So all you have to do, all you can do is do some randomization. So suppose we have a assignment rule where we select 2 elements from the 4 and assign treatment, and the others assigned to control. Okay. Then same way, we have how many possible combinations for that? Well, 4 combination 2, which is 6, right? We have 6 possible ways of assigning that kind of treatment. So this is basically the all possible assignment. So 1, 2, for example, case 1, 2, element 1 and 2 belong to get the treatment, and element 4, 3 and 4 get the control, or something like that. And then we can estimate it, right? We can we can compute. Basically, we don't know their probability distribution yet, because we don't have any probability at this point. But we still use formula to compute the estimators, right? So we still can compute the estimators. So for example, case 3, this is a treatment. So treatment mean, group mean, which is y. So potential outcome is 1, right? So, and then it is control group. Case 3. So then y1, 1, y1, 1 is 4. So this one is 4. Y4, 1 is 8. Y2, 0 is 3. Y3, 0 is 5. So then 12 divided by 2, 6. 8 by 2, 4. 6 minus 4 is 2. Okay. And now, this one is not really statistics, right? We just, here is just algebra, mathematics, right? We just the calculation. But now we assign probability and have some statistical meaning. So now we assign a probability rule, which is the simplest one is just a completely randomized experiment, which basically corresponds to simple random sampling, right? So discrete probability distribution, and then you can get this distribution, and then you can get expectation, right? So for example, tau is 1/6 minus 0.5, 1, 2, 3, 4, 5.5. So which is 15 divided by 6, which is 2.5 something, which is exactly 2.5. Okay, 2.5, right? So that means this is unbiased. Variance, you can do the, right? You can do the variance. So, but I skip. Okay. So exactly the same, right? Exactly the same as what we did for sampling design. So no model assumptions of Y. Example, we don't assume Y. For this randomization, we just roll the dice. That's it. And it's called design-based approach in survey sampling, but in causal inference and machine learning, they call it agnostic approach. So they are very good at make the name fancy make there's something make a new name and make some new brand, make a new brand essentially. Okay, so why? So essentially design-based approach. The reference distribution is the sampling distribution generated by the repeated application of the given selection mechanism. And why we are doing that? Well, it creates. So this is actually a gold standard, I'd say. Like probability sampling in survey sampling, right? So actually I have some table. Okay. So in survey sampling, finite target population is finite population, but causal inference, they are probably not really interested in that particular finite population, right? They are more interested in the effect of treatment over control. So they are conceptually thinking of infinite population. So parameter of interest is usually in survey sampling, descriptive parameters such as finite population mean or total, something like that. But causal inference, they are more interested in the causal parameter. So both method approach has a gold standard. So gold standard means that it's a model free and very objective, and which is designed. So in survey sampling, we call it probability sampling. In causal inference, it is essentially randomized experiment. But they are expensive. So gold standard is expensive, right? And very difficult sometimes. People may not respond. So non-response, for example. So even though you select the probability sample, what if they don't, collaborate, right? Decline. What if they decline? Then really we cannot really force them to participate, right? So that is a big problem, non-response. So we can call it partial failure, because we did apply randomization, but somehow you're not able to obtain the measurement that we want. Another issue in the context of causal inference, the same thing happens for non-compliance. Okay, even though the doctor, give a description, give some guidance to take for example, a particular medicine, but what if they don't eat, right? And so suppose you have some kind of experiment, even though it's in the beginning of the year, you are very eager to do exercise, and so suppose you assign to physical training, 30 minutes every day, something like that. But then as times go by, they may not, follow the guideline, right? So that is a typical non-compliance. So partial failure. And so this is a gold standard, and so this is kind of a weak failure. This is a strong failure in some sense, right? So the observational study, we have to assume some model and make a strong assumption which cannot really verify from the data, but build some conclusion under the assumption that we make. Same thing happens to non-probability sample. Even though we know that non-probable sample does not really have representative sample, but still, for several reasons, we commercial, especially the commercial vendors prefer to use non-probability samples. Then the conclusion from the data, it depends on the model assumption. There's some interesting concept. So Fisher randomization test. So suppose my null hypothesis is that tau I equal to 0. Okay, no treatment effect. Okay, so you may see. So this, we are not really thinking of random variable here. So this is a kind of a why potential outcome, not as a random variable, but just a value, realized value in the population. The idea for FRT is that under the null hypothesis, this particular null hypothesis, we can construct the sample distribution for any test statistic. That is a very interesting idea, actually. So suppose so like this two example, we know all the possible enumeration, right? Possible enumeration. But the problem is, so here, this is the possible enumeration. So this is actually T, sorry. But under the possible enumeration, we may have a different potential outcome, right? Because we have a different treatment assignment. But key part observation is that under the strong null hypothesis, they are all equal. So usually they are different, right? Because you have a treatment and control, you have a different potential outcome. But under the null hypothesis, there's no treatment effect. So that means your potential outcome between the treatment and control are the same. So that means you can actually, even though this was originally different, this part is no problem, right? You can always create the randomization. This part is tricky. The second part is tricky, but on the H null you can obtain. So that means you can compute. So you can basically compute from the realized sample and compute the p-value. So that is basically the idea. And so then the p-value measures the extremeness of the value of the realized test statistic with respect to the randomized distribution. But if the sample size is large, then the all possible combination is not computationally attractive. So then we may have rely on Monte Carlo method. But that's the all for today. Any questions? I think that's probably enough for today. And we'll see you next week. See you next week.